Welcome to this lecture of number theory. We will begin this lecture with a partition of a set. It is defined in this way. Partition of X is a collection of subsets of X, X1, X2, X key of X, such that the first condition on this collection must be Xi is not equal to 5. That means all of these subsets have to be non-empty. Second, they must be pairwise disjoint. And third, their whole collection or whole union must be the whole set X. That is, Xi's are exhaustive. We will take an example. Let's write partitions of X equal to, suppose a set containing only two elements A, B. Then partitions are, suppose the first partition P1, it is the collection of subsets A, B. Now both of these subsets are non-empty and their union is the whole X and their intersection is pi. Now another partition can be treated like this. We can take the whole set A, B. So these are the only two possible partitions of a set with two elements. And there is in fact an easier way to find out the number of partitions of a set with n elements. We will do it like this. Now on this first column we will denote the number of partitions of a set with one element. Now obviously it has only one partition by definition. Now a set having two elements. So P of 2 will denote the number of partitions of a set with two elements. Now what we have to do, we have to bring this one here. Now add up these two numbers and write the sum of these two numbers 2, that's here. Now this 2 is the number of partitions of a set with two elements. Now similarly, the number of partitions of a set with three elements is denoted by P of 3. Now for what we do here, we will bring this 2 here, we will write this 2 here. Now add up these two numbers and write down the answer here, which is 3. Now add up these two numbers and write down the answer here, which is 5. So this 5 is the number of partitions with three elements. Now next we need to find the number of partitions with four elements. What we do, we write down this 5 here, below this 2. Now add up these two numbers, we get 5 plus 2 is 7. We write that 7 here. Then add up these two numbers, we get 7 plus 3, that is 10. Now add up these two numbers, we get 10 plus 5 is 15. So therefore 15 is the number of partitions that a set with 4 elements has. So a set with 4 elements has 15 partitions. Now let's come to our next topic. Highest exponent that an integer divides n factorial. We mentioned this in the form of a theorem. The largest integer t such that p power t divides n factorial is given by t equal to summation k from 1 to infinity n divided by p power k, where this function denotes the greatest integer function. We similarly write another theorem here. The largest exponent of p such that the largest exponent t of p such that p power t divides 2n factorial divided by n factorial whole square is t equal to summation k from 1 to infinity 2n divided by p power k, greatest integer of this one, minus 2 times n divided by p power k. And if this p belongs to this set n is less than p is less than 2n, then t is equal to 1. Then t is equal to 1. So we have the largest exponent t of p such that p power t divides this 2n factorial by n factorial whole square. It is given by this formula. But if p lies between n to 2n, then t is always equal to 1. Now let's take up one small exercise here. Find the number of zeros at the end of factorial 2025. Now here we need to understand first, a 0 is obtained when we multiply a number by 10, or a 0 at the end of an integer means 10 divides that integer. And obviously the number of zeros at the end of an integer means that number of times 10 is a factor of that integer. So we need to find out the number of 10s as factors of 2025 factorial. Now every 10 is obtained as 2 into 5. To find number of zeros at the end of 2025 factorial, it is sufficient to find highest exponent that 5 power t divides 2025 factorial. Now how do we do that? We do it like this. It is summation k running from 1 to infinity 2025 divided by 5, this sum 5 power k. Now how do we do it? The first term here will be 2025 divided by 5. Then plus second term will be 2025 divided by 5 square, then plus so on. Now how do we quickly evaluate the sum? First of all, we write 2025 divided by 5. Now divide this by 5, this is equal to 405. Now divide this 405 by 5 and divide this sum, this is equal to 81. Now divide 81 by 5, this will be equal to 16. Now divide 16 by 5, this is equal to 3. So once we obtain a number less than 3, then we have to stop. And now add these numbers. Now 405 plus 81 plus 16 plus 3. So then this is the required highest exponent of 5, that 5 power t divides 2025 factorial. So this is our value of t. Now we don't need to find the number of 2's involved also, and because obviously the number of 2's will be more than the number of 5's in 2025 factorial. Now let's mention some results here that we must remember. The first one is this a1 plus a2 plus so on plus an factorial divided by a1 factorial into a2 factorial into an factorial is always an integer. Second, if n is a perfect number, then summation d divides n 1 divided by d, this is always equal to 2. So for a perfect number, the sum of reciprocals of divisors is equal to 2. The third one is, which is given by Gauss, this states that summation d divides n pi of d, this is equal to n. That means when we evaluate the phi function on all the divisors of a positive integer n, then the sum of all those pi d's is equal to the integer n. Similarly, another one is summation d divides n. Now tau d. Tau d means the number of divisors of d power 3. This is equal to summation d divides n tau of d whole square. Now let's define Mobius function, which is another number theoretic function defined as denoted by mu of n. And this is defined as mu of n is equal to 1. If n is equal to 1, this is equal to 0. If p square divides n power some prime p, and this is equal to minus 1 power k, if n is equal to p1 into p2 into pk. Let's take an example here. This mu of 1, by definition, this is equal to 1. Now suppose mu of 4, which is defined as mu of 2 square. Now since 2 square divides 4, so this is equal to 0. Mu of 6, this is mu of 2 into 3. Now this 6 is a product of two distinct primes, and there are two primes involved, so it is minus 1 square, that is equal to 1. Similarly, mu of 12, that is equal to mu of 2 square into 3. So here it has a repeated factor, so this is by definition equal to 0. And similarly, suppose mu of 30, that is mu of 2 into 3 into 5. Now it is a product of three distinct primes, so it is minus 1 power 3, that is equal to minus 1. And this has property that mu n is multiplicative, that is mu of mn is equal to mu m into mu n whenever these two integers are relatively prime. Now another theorem related to this Mobius function is, for each positive integer n greater than or equal to 1, summation d divides n mu of d, this is equal to 1 if n is equal to 1, and this is equal to 0 if n is greater than 1. So therefore this summation d divides n mu of d has only two values. Its value is 1 if and only if n is 1, otherwise this is always equal to 0. So again, let's take up some examples here. Suppose we want to define summation d divides 4 mu of d. Now 4 has the positive divisors 1, 2 and 4. So this is mu of 1 plus mu of 2 plus mu of 4. Now mu of 1 is 1, mu of 2 is minus 1, and mu of 4 is 0. So the sum is 0. And similarly, summation d divides 10 mu of d. This will be equal to mu of 1 plus mu of 2 plus mu of 5 plus mu of 10. Now mu of 1 by definition is 1, mu of 2 is equal to minus 1 because there is minus 1 power 1, mu of 5 is also minus 1 power 1, and mu of 10 that is minus 1 power 2. So now this again equal to 0. Okay, now we mention the Mobius inversion formula. Mobius inversion formula states that let f and small f be two number theoretic functions related by fn is equal to summation d divides n f of d. Then this f of n, small f of n, which is involved here on the right hand side of this definition, then this f of n is equal to summation d divides n mu of d into f of n by d. And this is also equal to summation d divides n mu of n by d into f of d. So here we need to understand it properly. We are given two number theoretic functions, capital F and small f, related by this relation. So here we have capital F of n on the left hand side and small f of d on the right hand side. So here this sum is running over the divisors of n, but now then what happens using the Mobius function? This f of n on the right hand side, f of n, it is defined as summation d divides mu of d into f of n by d. So that is the Mobius inversion formula n by d here. And similarly mu of n by d into f of. Let's make one simple result here. So we have the result using this Mobius inversion formula. We have this tau of n, that is the number of divisors of n. We can define it as summation d divides n 1. So summation d divides n 1, this always equal to tau of n, because for every divisor we will add up 1 here. Now tau of n is a number theoretic function. 1 itself is also a number theoretic function. So we can apply the Mobius inversion formula and see what happens. Similarly, we can write sigma of d, that is the sum of divisors of all the divisors of n, which is equal to summation d divides n d. So sigma of n is equal to summation d divides n adding d. Now using the Mobius inversion formula, we obtain. Now first applying the Mobius inversion formula to this one. So let's treat up this function as f of n, and let's treat this function as f of n. F of d. So this is our f of d here. Now f of d is just defined equal to 1. So on the left hand side, now using the Mobius inversion formula, we will have 1. This will be equal to summation d divides n mu of d into tau of n by d. Now this can be directly asked in the exam. What is summation d divides n mu of d into tau of n by d? And now using the Mobius inversion formula for simply this result, we will get this is equal to 1. And similarly, when we apply it on the second hand, now here we have d, so we treat this as f of n, and this treat as f of d. Now applying the Mobius inversion formula, this f of d becomes n here on the left hand side. So this is equal to summation d divides n mu of n by d into sigma of d. So that is the Mobius inversion formula that gives the value of n in terms of the Mobius function. Now some more results. The first one is mu of n into mu of n plus 1 into mu of n plus 2 into mu of n plus 3. This is always equal to 0. For n greater than or equal to 3, summation k from 1 to n mu of k factorial. This is always equal to 1. Summation t divides n mu of d into phi of d. This is equal to 0. Now let's come to our next topic, primitive roots. Before stating the primitive roots, we mention one definition here, un. It is a set of elements in Zn such that x and n are relatively prime. For example, if we want to write down u10, so this will be the set of elements in Z10 which are relatively prime to 10, so it is 1, 3, 7, 9. Now what does it mean by defining un? So un is the list of or the set of elements of Zn that have multiplicative inverse. Now we define the primitive root. An element a belonging to un is a primitive root of n if pi n is the smallest positive integer such that a power pi of n is congruent to 1 modulo n. So how do we define a primitive root? This is an element of un for which pi of n is the smallest positive integer which satisfies a power pi n is congruent to 1 modulo n. Or in other words, we can define it in group theoretic terms. In other words, a belonging to un is a, now we shall denote PR by a primitive root, is a primitive root of n if order of a is equal to phi n. And by definition of order of an element of a group, we mean it is the smallest positive integer that satisfies a power phi n is congruent to 1 modulo n. Now we can define it again in another way. So now what is the order of un? Now the order of the set un by definition, this is equal to phi n. Now we call an element of un as a primitive root if it has order equal to phi n. So thus generators of un are the primitive roots of n. In other words, we can also define it as, in other words, if un is not cyclic, then From group theory, we know that it cannot have an element of order n, then un has no, then n has no primitive root. Now we can also use the group theoretic terms to find what is the number of primitive roots. For that thing, we know number of generators of a cyclic group of order n is equal to phi n. But now here our group un has order phi n. So if un is cyclic, then n has a primitive root, and in this case, a number of primitive roots equals number of generators of un, which is equal to phi of order of un, that is phi of n. So therefore we have a formula for finding out a positive integer n which has a primitive root and which does not have a primitive root. So what are the integers that have primitive roots? They are precisely those integers n for which un is cyclic. And if un is not cyclic, then n has no primitive root. And in case un is cyclic, then it has a primitive root, and the number of primitive roots is equal to phi of n. Now let's come to some theorems regarding these primitive roots. We mentioned just two theorems here, and they are sufficient for finding the primitive roots of any positive integer n. If g is a primitive root of p and p square does not divide g power p minus 1, then g is a primitive root of p square. This result means that if g has order phi of p in up and p square does not divide g power p minus 1, then in up square g has order phi of p square. And the second result that we need to find the primitive roots, if g is a primitive root of p square, then g is a primitive root of p power k for all k greater than or equal to 2. So these are the two results. So what we need to do in order to find out the primitive roots of p power k, we just have to check if p has some primitive root. If p has a primitive root, then we will check if p square divides g power p minus 1. If this condition holds true, then g will be a primitive root of p square. But if g is a primitive root of p square, then g is a primitive root of p power k. So the process for finding the primitive root of p power k is we first need to find the primitive root of p. That's easier to handle. Then make this condition if this is true. If this happens to be true, then this g will be a primitive root of p power k. So now first let's find out a primitive root of some integer. Find a primitive root of, let us write down primitive root of 3. Solution. We have this u of 3. It is equal to 1, 2. Now it is very easy to handle. We have a group of order 2. It is obviously a cyclic group. It will have one element of order 1 and one element of order 2. Now since this 1 is the identity element, so its order must be equal to 1. So we are left with 2 here, that is order 2. Order of 2 is equal to phi of 3, which is equal to 2. And in fact we can also verify it. We have 2 power 1 is congruent to 2 modulo 3. That means order of 2 is not equal to 1. Then 2 square is equal to 4, and 4 is congruent to 1 modulo 3. So therefore 2 is the smallest power of 2 such that 2 square is congruent to 1 mod 3, means 2 is a primitive root of 3. Now the question is, if we are asked find primitive roots of 27, which is equal to 3 power 3, which we have deliberately chosen as 3 power 3 because we already have primitive root of 3 is equal to 2. Now using these above results, now in order to find primitive roots of 27, we will first find the primitive root of 3, that is equal to 2. Now we will see if this condition is true. So now here primitive root of 3 is 2, which is our g. Now let's check if p square divides this g power p minus 1, then this g power p minus 1, this is 2 power 3 minus 1, so it is 2 power 2 minus 1, which is equal to 3, and p square is equal to 9. Clearly, then hence this p square does not divide g power p minus 1, because 9 does not divide 3. We have to check 9 divides 3 or no. 9 does not divide 3. This implies 2 is a primitive root of p square, and p square is equal to 9 here. Now let's try to verify it also, if 2 is really a primitive root of 9 or not. Now first of all we will write u9. u9 is equal to 1, 2, 4, 5, 7, 8. So order of u9 is equal to 6. So we must have 6 is the smallest positive integer such that 2 power 6 is congruent to 1 modulo 9. So which is actually the value of phi of 9. So now let's begin with evaluating like this. 2 is congruent to 2 mod 9. Second, 2 square is congruent to 4 mod 9. 2 cube is congruent to 8 mod 9, which we can write as minus 1 mod 9. Now let's look at this group again. It has factors like 1, 2, 3 and 6. Now the orders of elements in U9 will either be 1, 2, 3 or 6. It cannot be 4 and 5. Now order of 2 is not equal to 1 because it is 2, it is not 1. Order of 2 is not 2 because it is congruent to 4. 2 power 3 is 8, that's minus 1, so order of 2 is not equal to 3. So therefore the only choice now left is 6. So this implies order of 2 is 6 in U9. So that means 2 is a primitive root of 9. That is 2 is a primitive root of 9. But now how many primitive roots does 9 have? Now using the formula, now 9 has phi of 9, which is equal to phi of 6, which is equal to 2 primitive roots. Now how to find the other primitive root of 9? That's our one exercise, how to find other primitive roots of 9. So that's our one question. Second is, actually we want to find the primitive roots of 27. Actually here we using g equal to 2. We will use this earlier primitive root obtained as a primitive root of 3 to find the primitive roots of 9, or we can directly go to 27 and use this 2 to find the primitive roots of 27. So let's not find the primitive roots of 9 here, so that will be left as an exercise. Here we will just find the primitive roots of 27, or we can even write 3 power 4, that's 81. Now let's mention some result here and try to understand how do we find the primitive roots of higher power of p from using the primitive roots of just the primitive roots of p. Again employing the group theory. If A belongs to G, where G is a finite group, if A is an element of G where G is a finite group, then if we want to find order of A power k, this is equal to order of A divided by GCD of k and order of A. Now let's try to use these things here. Now for primitive roots, how do we use this result? For primitive roots, we can use the same result. So given G is a primitive root of P, that is order of G is equal to phi of P in UP. So G is a primitive root of P. We want to find the primitive root of P power k. Now what we do to find primitive root of P power k using G, we have this procedure. So find all j such that j is relatively prime with phi of P power k. We have to find all integers j which are relatively prime with phi of P power k. Then primitive roots of P power k are g power j such that j and phi of P power k are relatively prime. Now how we are using this result using the order of an element of A power k in a group? Now here instead of A we have G. Now order of G power j. Now here order of G power j. This will be equal to order of G divided by GCD of j comma order of U of P power k, that is phi of P power k. Now as we know order of G is a primitive roots, order of G is equal to phi of P power k divided by, now j and phi of P power k, we are deliberately choosing j which is relatively prime with phi of P power k, so this is equal to 1. So this is phi of P power k. So therefore if G is a primitive root of P, then G power j is a primitive root of P power k, provided this j is relatively prime with phi of P power k. Now using this thing here, now from above 2 is a primitive root of 3. Now to find primitive roots of 27, which is equal to 3 power 3. So what we do, we find phi of 27, which by definition is pi of 3 cube. This is equal to 3 cube minus 3 square, that is 27 minus 9, that is equal to 18. Now j and 18, we must have j and 18 should be relatively prime. So this implies j is equal to 1, j is equal to 5, j is equal to 7, then 11, then 13, and then 17. So these are 6 numbers which are relatively prime with j, which actually this set actually forms U18. We don't need to mention that U18 here, so this U18. So hence primitive roots of 27 are, so it is 2 power 1, 2 power 5, 2 power 7, 2 power 11, 2 power 13, and 2 power 17. So these will be the 6 primitive roots of 27. Now we finally take up this theorem. An integer n greater than 1 has a primitive root if and only if n is equal to 4 p power k or 2 p power k, while p is an odd prime. Now in fact here we can remember that these are the only 4 possible values of n for which un is cyclic. Next we solve this exercise. Find all primitive roots of 26, and we can write 26 as 2 into 13, so it has a primitive root because it follows in this list 2 into p power k. Now next exercise is given that 3 is a primitive root of 5, which can also be verified that 3 power 4 is congruent to 1 modulo 5. So that 3 is a primitive root as it has order equal to 5 of 5, which is equal to 4. Using this 3 as a primitive root of 5, we have to find all the other primitive roots of 5. The next question is, using this primitive root 3, we have to find all the primitive roots of 25. Okay, let's first take up the Euler's theorem that we had skipped. If a and m are relatively prime, then a power pi m is congruent to 1 modulo m. We also take another result, that is by Gauss. This state is for n greater than 1, summation d divides n pi of d, this is equal to n. And third one, for n greater than 1, the sum of elements of un equals n phi n by 2. So this can also be stated in a way that for n greater than 1, the sum of integers, the sum of positive integers less than n and relatively primed n equals n phi n by 2. Now the fourth one is, which is related to the Mobius function, this is summation d divides n minus 1 power n by d into phi of d, this is equal to, this is related to the phi function, this is equal to 0 if n is even, and this is minus n if n is odd. Okay, now with this revision we begin to define the universal exponent. Universal exponent is defined in this way: if n is equal to 2 power alpha naught, p1 power alpha 1, p2 power alpha 2, pk power alpha k, which is the prime factorization of n greater than 1, then the universal exponent is defined as, this is the general definition, lambda of n, which is defined as LCM of lambda of 2 power alpha 0, phi of p1 power alpha 1, so on, pi of pk power alpha k, where these pi's are all primes, and lambda of 2 is equal to 1, lambda of 2 square is equal to 2, lambda of 2 power k is equal to 2 power k minus 2 when k is greater than or equal to 3. So this is how do we define the universal exponent. Now its properties: for n equal to 2, for p power k and 2p power k. 2p power k, this lambda of n is always equal to phi of n. Now there is a generalization of Euler's theorem which states that if a and n are relatively prime, then a power lambda of n is congruent to 1 modulo n. Okay, now let's take up one more result here, that is a theorem. Let n be an integer, let n has a primitive root. So n is an integer of the form 2 for p power k or np power k, and let a and n are relatively prime. If a and n are relatively prime, then the congruence x power k congruent to a modulo n has a solution if a power pi n by d is congruent to 1 modulo n. Now we check this theorem in case of an exercise. Check if the congruence is x power 3 congruent to 4 mod 13 and x power 3 congruent to 5 mod 13 have a solution or not. Now we can solve these congruences using this above theorem. So in the solution, for the first congruence x cube congruent to 4 mod 13. So we compare here k is equal to 3, a is equal to 4 and n is equal to 13. We have forgotten to mention here that this d is the GCD of k and phi n. So now here we have first of all this n is equal to 13. So phi of n is equal to 12. So GCD of k and phi n, this is equal to GCD of 3 and 12, which is equal to 3. So this is our d here. So now what we need to do, we need to evaluate a power phi n by d. So now let's evaluate phi n divided by d. So it is 12 divided by 3, which is equal to 4. So now let's evaluate a power pi n by d, that's a power 4, which is equal to 4 power 4, which we had to evaluate in modulo 13. If this is congruent to 1, then it has a solution. If it is not 1, then it does not have a solution. Now we can write this 4 power 4 as 4 square into 4 square. Now 4 square is 16. 16 is congruent to 3 mod 13. And second 16 also 3 mod 13. So this finally becomes congruent to 9 mod 13. 9 mod 13. So which is not congruent to 1 mod 13. So this implies x power 3 congruent to 4 mod 13 has no solution. Now similarly for the second congruence, we just have to change the value of a, remaining is all same. Now for a to be 5, we can write 5 power 4 mod 13. We need this to be 1 or not 1. If it is 1, then it has a solution, which is congruent to 2. Now 5 power 4 can be written as 5 square into 5 square mod 13. Now 5 square is 25, that is equal to 1 mod 13. 25 is congruent to minus 1 mod 13. And second 25 is also congruent to minus 1 mod 13. Now minus 1 into minus 1 is plus 1 mod 13. So this implies the congruence x power 3 congruent to 5 mod 13 has a unique solution. Sorry, not unique, but has a solution. So we can just prove using these results whether it has a solution or not. Now let's come to define the quadratic residues. Quadratic residue is defined as an integer a belonging to n is a quadratic residue. Now from here onwards we will use the notation QR for denoting the quadratic residue if x square congruent to a modulo n has a solution. In fact, quadratic residue of n, if x square congruent to a mod n has a solution. Otherwise, a is a quadratic non-residue. Quadratic non-residue. And for simplification, we write quadratic non-residues as q and r. Now results regarding the quadratic residues and the quadratic non-residues, and later on we will see how to find the integers which are quadratic residues and quadratic non-residues. But right now we will include these theorems that are also necessary for any kind of entrance examination. So the first one is necessary and sufficient condition for a quadratic residue. For a quadratic residue is a power p minus 1 by 2 is congruent to 1 modulo p. So this is necessary and sufficient condition for a to be a quadratic residue of p. And second is necessary and sufficient condition for quadratic non-residue of p is a power p minus 1 by 2 is congruent to minus 1 mod p. Now another result that we want to mention here is there are p minus 1 by 2 quadratic residues of p and p minus 1 by 2 quadratic non-residues of p. So this means that half the numbers of integers from 1 to p minus 1 are quadratic residues and the other half are quadratic non-residues. Now another result that we want to mention here is that a is a quadratic residue of n, a is a quadratic residue of m if a power pi m divided by 2 is congruent to 1 modulo. Otherwise, A is a quadratic non-residue. otherwise A is a quadratic non-residue. So this is a very nice theorem here. A is a quadratic residue of m if a power pi m by 2 is 1, otherwise A is a quadratic non-residue. So therefore, in order to check whether a given integer is a quadratic residue of m or not, we just need to verify a power pi m by 2 is either 1 or minus 1, is either 1 or not equal to 1. This actually comes from this theorem here that we have mentioned here at this stage. This theorem implies this result e power pi m by 2 should be congruent to 1 modulo m. Now next result that we want to mention here is, let P be an OR prime if P is congruent to 1 mod 4, then the product of quadratic residues of P is, then the product of quadratic residues of P is congruent to minus 1 mod P, and if P is congruent to 3 mod 4, then product of quadratic residues is congruent to 1 modulo P. Now next result that we must remember, if P is greater than 3, then the sum of quadratic residues is divisible by P. And the last one, if P is greater than 2, and A is a quadratic residue of P, then A is a quadratic residue of P power alpha for all alpha greater than or equal to 1. So still we have not calculated how to verify whether a given integer is a quadratic residue or not with an exercise, but we will take up later on again. Now before taking up exercises on the quadratic residues, we will first define the Legendre symbol. Legendre symbol, this is defined as, let P be an integer greater than 2 and A is relatively prime with P, then we define this A by P, which we call the Legendre symbol, as 1 if A is a quadratic residue of P, and we define the symbol as minus 1 if A is a quadratic non-residue of P. So therefore here we have some nice theory as how to evaluate whether a given integer A is a quadratic residue of a prime or not. So we just had to evaluate 1A by P. If it is 1, then it's a quadratic residue. If it is minus 1, then A is a quadratic non-residue. Now here we have some properties of this Legendre symbol that we shall take in the form of a theorem. It has the first case as A by P is always congruent to A power P minus 1 by 2 modulo P. Now second, A into B divided by P, where A and B are two integers, they are not necessarily prime, they can be any two composite numbers. This is equal to A by P into B by P. So therefore we can write this as a product of two functions. Now the third one is, if A and B are congruent, they are congruent to mod P, then these numbers will either be both quadratic residues or both quadratic non-residues. So they will always have the same value in their case. And the fourth property is, we have like this, A square divided by P is always equal to 1 by P, which is actually 1 square by P also, that's also equal to 1, and minus 1 by P, that is equal to minus 1 power P minus 1 divided by 2, and this can also be proved using this part number 1. Okay, now using these properties we can come to an exercise. Evaluate if 30 is a quadratic residue of 31 or a quadratic non-residue of 31. So what we will do, in the solution we are actually asked to evaluate 30 divided by 31. Now as we know that 30 is congruent to minus 1 mod 31, so we can write this as minus 1 by 31. Now using this result here, this can be written as minus 1 power 31 minus 1 divided by 2. So it is minus 1 power 15, which is equal to minus 1. This implies 30 is a quadratic non-residue. 30 is a quadratic non-residue of 31. Now let's take up the second exercise. evaluate 8 divided by 11. Now by definition this is equal to 2 square divided by 11 into 2 divided by 11. Now 2 square by 11 is equal to 1 because a square by b is always equal to 1. So this is just equal to 2 by 11. Now for this 2 by 11, what we need to do, we can use this first part. A by p is congruent a power p minus 1 by 2 mod 1. So we need to evaluate this 2 power 11 minus 1 by 2. If this is 1 or minus 1, accordingly we can see this 8 is a quadratic residue or quadratic non-residue. So this becomes 2 power 5, which is equal to 32. Now in mod 11, this is equal to minus 1 mod 11. So therefore this is equal to minus 1. That means 8 is a quadratic non-residue of 11. Now here we take Gauss lemma, which gives another method for evaluating an integer to be a quadratic residue or a quadratic non-residue. So this states that if a and p are relatively prime, consider the residues a, 2a, 3a, so on, p minus 1 by 2 into a. And we have to evaluate all of them in modulo p. Then if k numbers in this list are greater than p minus 1 by 2, it is strictly greater than, then a by p is equal to minus 1 power k. So therefore this is a very easy way to handle the quadratic residues or a quadratic non-residues. Suppose we want to evaluate minus 48 divided by 31. Now this is equal to, first of all, minus 1 into 2 square into 2 square into 3 divided by 31, which is equal to minus 1 by 31, then 2 square by 31, then 2 square by 31, then 3 by 31. Now we know that minus 1 by 31 is already evaluated to be minus 1, 2 square, they are both giving 1, and so we finally get 3 divided by 31. So it is minus 3 divided by 31. So we are left with the case 3 divided by 31. So now we will use this 3 divided by 31 and we will solve it using the Gauss lemma. So what we have to do in Gauss lemma? So using Gauss lemma, we have to evaluate a, that is 3 here. So here we have a is equal to 3 and p is equal to 31. So p minus 1 by 2, that is equal to 15. So we have to evaluate this a into 1, a into 2. So we have 3 into 1, then 3 into 2, then 3 into 3, up to 3 into 15. And we have to evaluate all of them in modulo 31. So this is equal to 3, then 6, then 9, then 12, 15, 18, 21, then 24, then 27, then 30. Now these are all reduced in modulo 30. Now the next number will be 33, which is congruent to 2 mod 31. Next number will be 36, which is congruent to 5. Next number will be 39, which is congruent to 8. Then there will be 42, which is congruent to 11. The last number is 3 into 15, that is 45, which is congruent to 11 plus 3, that is 40. So now let's look for the numbers which are bigger than p minus 1 by 2 modulo 31. So p minus 1 by 2 is 15. So we have to look for the numbers which are bigger than 15 but in modulo 31. So bigger than 15 is 18, 21, 24, 27, 30 and now not 33. So therefore these are the numbers which are bigger than p minus 1 by 2 modulo 15, modulo 30 actually. So these numbers are 5 in number. So thus this minus 3 divided by 31, this is equal to minus 1. First of all, this is this minus 1. Now 3 by 31, it is minus 1 power 5. So it is minus 1 into minus 1, this is equal to plus 1. That means minus 48 is a quadratic residue of 31. Now we mention one more theorem here. If 2 is a quadratic residue of p or not, so this is 2 divided by p, the legendary symbol. This is equal to minus 1 power p square minus 1 divided by 8. Now let's write down the quadratic reciprocity law. This states that if p and q are odd primes, then p by q into q by p, this is equal to minus 1 power p minus 1 by 2 into q minus 1 by 2. Okay, now we take up one important result regarding this quadratic reciprocity. It states that this legendary symbol p by q, this is equal to minus p by q. So this is equal to minus q by p if p has the form 4k minus 1 and q has the form 4l minus 1. That means if both odd primes p are of the form 4k minus 1 and 4l minus 1, then p by q is equal to minus q by p. Otherwise this is same as q by p plus q by p if otherwise. So in order to use this result, we just have to verify whether p and q are both of the form 4k minus 1. Then we have to reciprocate it and write minus, otherwise we have to write q by p. So now here we can see how powerful this tool is to evaluate the quadratic residues. Now in the earlier question we had taken up the case of 3 divided by 31. Now 3 and 31 are both odd primes. So now using this form of P and Q, now here P has the form 4k minus 1 because this is 4 minus 1. But in the denominator Q, that is not of the form 4k minus 1 because 31 plus 1 is 32 and 4 does not divide 32. So we can write this as 31 divided by 3. But now what happens here? Here now we have to use the moduli P, that is moduli 3. So this is equal to, we can divide this 31 by 3 and get the remainder, that is equal to 1. So this becomes 1 by 3 because now modulus is 3 and we know 1 by 3 is equal to 1. So this is how the things become easy using this quadratic reciprocity. Or we take another example using this quadratic reciprocity. We evaluate 19 divided by 61. Now both of these are prime numbers and obviously it becomes difficult to use a power p minus 1 by 2 or like results. But here we have the solution like this. This 19 divided by 61. Now 19 plus 1 is 20. So 19 is of the form 4k minus 1. 61 plus 1 is 62. It is not of the form 4k plus 1. So this is equal to 61 by 19. Now we have to divide this 61 by 19 because now we have the modulus with 19. Divide 61 by 19. This can be written as 57 plus 4 divided by 19. Now 19 is congruent to 0 mod 57 is congruent to 0 mod 19. So this is equal to 4 divided by 19 because 57 is same as 0. But now we can see this is equal to 2 square divided by 19 and a square divided by p is always equal to 1. So this is how the quadratic reciprocity law works. Therefore, in order to evaluate the legendary symbol of an integer, we have to use the quadratic reciprocity law and just few properties like a square by p is always equal to 1, 1 by p is always equal to 1, and minus 1 by p is equal to minus 1 power p minus 1 divided by 2. So these are the only three properties that we need to remember along with the quadratic reciprocity law to evaluate the legendary symbol as p by q. Now let's come to the Jacobi symbol. Jacobi symbol is if m and n are relatively prime integers where n is equal to q1 into q2 into qk, where qi's are prime but not necessarily distinct, then the Jacobi symbol m by n, this is equal to m divided by q1 into q2 into qk. This is defined as m divided by q1, which is the legendary symbol, then m divided by q2, which is a legendary symbol, into m divided by qk, where now this m divided by qi is a legendary symbol. So therefore this helps us to evaluate the quadratic residues or the quadratic non-residues or legendary symbols for the integers of the form m by n, while both m and n are composite. This again has a quadratic reciprocity law similar to what we had in the legendary symbols. This states that this p by q, where p and q are now not necessarily primes, they are integers which are relatively prime, p by q into q by p. This is equal to minus 1 power p minus 1 by 2 into q minus 1 by 2, while p and q have GCD equal to 1 but need not be prime. So this is a more generalized version of the quadratic reciprocity law which was given in legendary symbol. Now here we have some theorems. This again minus 1 divided by q. This is equal to minus 1 power q minus 1 by 2. And 2 divided by q. This is equal to minus 1 power q square minus 1 divided by 8. And moreover, we have one nice result regarding the quadratic residues and the quadratic non-residues of p. So it is j running from 1 to p minus 1 j divided by p. So the sum of the quadratic residues and the quadratic non-residues, this is always equal to 0 because half of numbers are quadratic residues and other half are quadratic non-residue. So whenever we have a quadratic residue, we get 1, and whenever we have a quadratic non-residue, we get minus 1. Now let's take up one more topic, that is the Feri fractions. For Feri fractions, we construct a table using 0 by 1 and 1 by 1 in row 1, which we call as R1. In the nth row, we first write all entries of n minus 1th row and then insert a plus a dash divided by b plus b dash between a pair a by b and a dash by b dash, provided this b plus b dash is less or equal to n. So this is the construction of a table actually. We start with the first row as 0 by 1 and 1 by 1. It has only 2 entries. Then in the nth row, we first write all the entries of n minus 1th row and then insert a by a plus a dash by b plus b dash between a pair of numbers a by b and a dash by b dash, but provided this b plus b dash remains less or equal to n. So now let's see how do we construct this table. So first of all, row 1 has entries 0 by 1 and 1 by 1. Now for row 2 we write this both of these entries first of all 0 by 1 and 1 by 1. Now this is a by b and this is a dash by b dash. Now 0 plus 1 divided by 1 plus 1, that becomes 1 divided by 2. So therefore, but this 2 is equal to 2 here, so we can insert this and there is only one pair here. Now for our 3, first we write all these 3. So we write 0 by 1, we write 1 by 2 and we write 1 by 1. Now between the 0 by 1 and 1 by 1 we will insert 0 plus 1 divided by 2, and between 1 by 2 and 1 by 1 we will insert 1 plus 1 divided by 2 plus 1. So therefore this row becomes 0 by 1, 1 by 2, then we again get 1 by 2. Sorry, this is equal to 1 plus 2. Then this becomes 3 here, then 1 by 2, then 2 by 3, then 1 by 1. Now in the fourth row, we first write all these entries of the row number 3. So it is 0 by 1, then 1 by 3, then 1 by 2, then 2 by 3, then 1 by 1. Now we have to insert the new numbers and keep in mind that the denominator should not be greater than 4. So now this is 0 plus 1 by 1 plus 3, this becomes 1 divided by 4. Now if we insert here, we get 2 by 5, but 5 is bigger than 4, so we cannot insert here. And similarly, we cannot insert here, and 2 by 3, 1 by 3, 1 by 1, this becomes 3 divided by 4. So we can insert these two numbers here. And now let's finally form row R5, which is equal to 0 by 1, then 1 by 4, then 1 by 3, 1 by 2, 2 by 3, 3 by 4, 1 by 1. Now we can insert here 1 by 5. Now here we cannot insert. Here we can insert 2 by 5. Here we can insert 3 by 5. Here we cannot insert, and here we can insert 4 by 5. So this is how do we construct the table, and these fractions that we obtain here, they are called Fari fractions. The properties of this table are, if GCD of x and y is equal to 1, then x by y appears in yth row and all preceding rows. Moreover, fractions are arranged in order of their size. So what does that mean? Like we have 1 and 2, they are relatively prime. So 1 by 2 appears in the second row. Now it will appear in every row from row second onwards. As we can see, 1 by 2 is here, then in the third row also, then in the fourth row also, and so on. Similarly, like 2 and 3, they are relatively prime. So 2 by 3 appears in the third row. Now it will appear in every row from row 3 onwards, and so on. Moreover, the fractions are arranged in the ascending order or the increasing size, as we can see here in the, like in this row, 0 by 1 it is equal to 0. Now 1 by 3 it is equal to 0.33 something. 1 by 2 it is equal to 0.5, that is bigger than 0.3. 2 by 3 that is 0.6, so it is bigger than 0.5 even, and 1 by 1 this is 1. The same thing happens in every row. The fractions are arranged in increasing order of their size. Now next property, if a by b is less than a dash by b dash are consecutive fractions. If we have these two consecutive fractions in some row, then the determinant of a dash, b dash, ab, this is always equal to 1. The third property is the terms on the left and right of 1 by 2 have the greatest odd integer in their denominator, which is less or equal to n. So actually in the nth row, the terms on the left and right have the greatest odd integer in their denominator less or equal to n. Now finally we write down one theorem to evaluate what is the number of terms in nth row of a Fari fraction, of a Fari table. The number of terms in nth Fari sequence is 1 plus summation j running from 1 to n pi of j, and the sum of all fractions in nth Fari sequence is exactly the half of this value. And finally one more property, a by b is less than a dash by b dash, then 1 divided by n into n minus 1 is less or equal to a dash by b dash minus a by b, and this is always equal to less or equal to 1 by n. So these were some details about these topics of the number theory. So here we conclude this lecture.